Good. Right. So we finished last class with the discussion of vaccines. And the main argument of my morning class today, when we were talking about doing the same thing, you know, that I'm an obnoxious parent, the main comment was that all my problems because I'm an idiot, which is pretty much true. Anyway, now we need to talk about T cells. We finished humoral immunity, and now it's T cells. So, before we move on to T cells, we need to figure out such thing as major histocompatibility complex. It's a mouthful, and usually I don't want to say anything really bad about people who write science textbooks, but I was always wondering why a lot of matters there are explained in such a confusing and complicating manner. You can start with a very simple idea of a concept and then add layers of complexity to it. So my purpose here is to this is pretty complex thing, but my purpose is to explain it to you in the discernible way. For this, we first have to figure out what does the word histocompatibility mean. Histo stands for tissues, and compatible meaning that whether the cells are coming from your tissue or they are foreign. Okay, so major histocompatibility complex, or acronym MHC, and I'm going to use that acronym, allows you to differentiate between self and foreign. Make sense? There are two types of MHC. MHC, you may ask, what is that? Those are proteins, molecules, okay, on the surface of the cell. And there are two types of MHC molecules. Type 1, and not very much surprisingly, type 2. Does that make sense? So type 1 is expressed or are expressed on all nucleated cells, which excludes platelets and red blood cells. Right? So what do they do normally? What type 1 MHC do normally? If this is the normal cell, there's a nucleus. A nucleus has DNA molecule in it, right? When cell grows, what happens to DNA? It gets it's before the cell divides, but when it's just growth, if it's not replication, then DNA is transcribed into RNA, right? And RNA is translated into the protein. Is that protein an antigen? Yeah, it can be. Okay, but in case of normal cell, it's a self-antigen. Immune system doesn't recognize it. Do you agree with me? So this protein, inevitably, proteins, they get chopped up in pieces, and those pieces, the antigenic determinants of these proteins, bind to the MHC class 1 on the cell surface. So what it does, it's actually written MHC class 1. So what it does, cell signals, I'm good, I'm fine. I'm self. Does that make sense? What happens if the cell becomes infected? Yes. Now, let's figure out how it does it. It doesn't just present the flag. Let's see how this flag goes there. It still has a nucleus, but not focusing on nucleus. So you have a pathogen here. And when a pathogen replicates, is the protein synthesis involved? Is there protein synthesis? Sure. And those proteins are inevitably going to be broken in pieces. So there are going to be fragments of those proteins. And those fragments, endogenous antigen. So what does endogenous mean before we move on? Endo. Endogenous means coming from the inside, from inside of the cell. Okay. This endogenous antigen binds to MHC class 1. So cell, from being normal, goes into the state when it starts to show that it's abnormal. Bless you. Does that make sense? Okay. We haven't heard the word T cell yet. We will. Not right now. So MHC type 1 presents endogenous antigens on nucleated cells of the body. Can we move on to MHC class 2? So type 2 MHC are on antigen presenting cells. Before we list them, antigen presenting cells, what do? They present antigen, yeah, that's their function. And which cells they present it to? T cells. Okay, we'll get to this point when we will compare T and B cells. So far, we need to line up three major types of antigen presenting cells. It's going to be dendritic cells, macrophages, and B cells. The presentation by antigen presenting cells, and we now going to focus on the dendritic cell. So dendritic cell, that's much better, it engulfs a pathogen okay, and breaks it in pieces. So it essentially acts as a phagocyte. But you have to, so dendritic cells are actually close relatives of the phagocytes. But what is the main purpose of the phagocyte? To destroy the cells. That's the job. For dendritic cell, it's not to destroy the pathogen. It's to take it in, break in pieces, and then present on its surface in complex with MHC class 2. I'm going to ask you a really tricky question. It's not actually tricky. Dendritic cells, macrophages, B cells, do they have a nucleus? Yeah, of course. So are they going to have MHC class 1 as well? Yes. So antigen presenting cells have both types of major histocompatibility complex molecules. Are we clear on that? Good? All right. This piece of information, is that understood? Because it will become very important to understand how T cells work. Well, let's figure out how T cells work. Where do they start? Bone marrow, right? So T cells in a bone marrow. And where do they go next? Yes, they go in the thymus to do what? To mature. Let me tell you something. T cells cannot directly recognize the antigen. What I mean by that, let's recall a little bit about B cell. So if you have a B cell, and it has a receptor, and this receptor is exposed to the pathogen. Oh, let's call it more broad, the antigen, okay? What's going to happen to B cell upon this exposure? It will, but in terms of the B cell activation, is it going to become plasma cell? Is it going to, yeah, so it's going to get activated. Does that make sense? So we have B cell activation. If you would try to do the same with a T cell, what's going to happen? Directly. If you directly expose T cell to the antigen, the answer is nothing. The reason for that is antigen has to be presented by MHC molecules. Does that make sense? So B cells, when they mature in the bone marrow, which quality is used to select for the right B cells? They have to be able to tell something apart. Yes, B cells have to differentiate between foreign and self. T cells, do they have to do the same? Do they have to differentiate between your own tissues and foreign tissues? Sure, but they also have to be able to do something else. When in thymus, the first act of selection is the first question that is asked. Can they recognize MHC? Does that make sense? So can they be presented with antigen? Will they recognize MHC molecules? There are two answers, as usual. Answer is no. And what's the consequence of the no answer? Apoptosis, cells die. Now, for yes, what is the now we're going to check if cells can actually differentiate self and foreign. Does that make sense? Now, again, two answers. If answer is no, then if they cannot tell apart self and foreign, they die. And if they can, where do they go? Lymph nodes and spleen, secondary lymphoid organs. What do they do there in lymph node and spleen? Bingo. They wait to be presented with an antigen. Where is the better place to wait for all the antigens rather than in the sewer? Because lymph node and spleen are parts of the sewage system of the body, parts of the lymphatic system. Does that make sense? So eventually they get presented with an antigen, and that causes differentiation, proliferation, something else? No, differentiation, proliferation. Okay, so they become specialized, they become more numerous. So far, so good. Well, let's figure out which types of T cells we have. So generally speaking, sorry. Generally speaking, we have two populations of T cells. So CD8, I think. No, CD4 would be logical to start with. And CD8. Okay? And, well, yeah, CD4 is logical to start with, but I will start with CD8 because it's simpler. CD8 cells, when they are presented with an antigen, they become killers. T killer or cytotoxic lymphocyte. What does it do? It kills other cells. Now, if it is presented by antigen presenting cell, if antigen is presenting to CD8 cell, can it recognize free floating antigen? No. The antigen on the diseased cell has also to be presented. Does that make sense? Remember we talked about MHC molecules that are present on all nucleated cells. Which type is that on all nucleated cells? Type 1. So CD8 cells, which are killers, which type should they recognize? Killers. They have to be able to kill any cell in the body. Which type, MHC type, should they recognize? Type 1. Does it make sense? Okay, we'll get, so via MHC1. Okay? We'll get to the mechanisms. CD4 cells. There are several populations of CD4 cells. The T regulatory cells and T helper cells. Okay, so these guys become differentiated when antigen is presented via MHC class 2. Does that make sense? All right. Of course, both populations will produce a set of memory cells. Okay. Those are going to be different memory cells, memory CD4 and memory CD8. The way to remember which cell type recognizes which MHC type, 8 by 1. 8 by 1 is 8. 2 by 4 is 8. That's my own mnemonic rule. I mean, it's up to you to use it or not. Okay, so far, are we okay? Now let's see what they do exactly. And first, we will focus on CD8 cells. So CD8 cell was presented with an antigen via MHC class 1, okay? And here it is. That's that cytotoxic lymphocyte. It becomes cytotoxic lymphocyte, okay? And it encounters cell that is infected, okay? Let's say it's a fibroblast, cell of a connective tissue. What type of MHC does it have? 1. Does that make sense? Let's picture it. And it has antigen presented on MHC1. Now that specific clone of cytotoxic lymphocytes can recognize this complex using T cell receptor. Does that make sense? And then it kills it. So how does the cytotoxic lymphocyte kill the cell? It doesn't phagocytose. But if it doesn't phagocytose, what else can it do? Good. It doesn't, unfortunately. How do we call the cell death? Normal cell death. Apoptosis. Lysis is often abnormal. When cell just explodes, it's not. Apoptosis is sort of regulated. Okay? So the cytotoxic lymphocyte can cause apoptosis using 2 different ways. One is by interaction between Fas ligand and Fas receptor. When they interact, Fas ligand on CD8 cell and Fas receptor on the infected cell, it stimulates apoptosis in the infected cell. That makes sense? So just intracellular signaling, and you have apoptotic genes, special proteins that in the very ordered manner dismantle the cell pretty much. Another mechanism is the release of granzymes and perforins. So here are the perforins that form what? Pore holes, yes, pores. And then granzymes can enter the cell and induce apoptosis. And granzymes too. So blue is granzymes and green is perforins. Okay. Oh, the apoptosis. There's a. I can't give you like all the proteins. The idea is that there are signaling proteins. One activates another, and then another, and another. The idea is that it goes all the way down to the nucleus. And the nucleus, it starts the transcription actually of certain genes, and the proteins that are produced, most of them are, the huge set of them is called caspase, which is calcium dependent serine protease. Anyway, those proteins will start to digest the cell from the inside. Okay? And also other proteins will start to cut the DNA in pieces. And actually, if you will take a cell population, somehow induce apoptosis, and then isolate DNA from that population and separate it and look at the fragments, they form apoptotic ladder, which is pretty standard. But that's a controlled death. So it's a controlled digestion of the cell from the inside. When cell just explodes, that's not controlled. And that's regular. Usually that's bad. Okay. Did I answer? Good. So that's what CD8 cells do. It's pretty straightforward, isn't it? Yes.
So what happens if some of those enzymes hit the cell next to it that isn't infected? Does it cause apoptosis in that cell next to it?
If hypothetically they would hit the uninfected cell, yes. But you mean the preference? The preference. Well, my picture doesn't. So it's not like perforins are thrown out of the boat and just swim to another cell. No, it's all very, very close. So it's pretty much a imagine. Remember we talked nerve signal transmission. There is a cleft between two cells, synaptic cleft, which is extremely narrow. So can hypothetically acetylcholine or epinephrine travel to adjacent neuron? Hypothetically, yes, but realistically, no, because the cleft is so small that it's like I'm throwing something from me to you. Chances that I will throw it this direction are fairly low. Does that make sense? So that's pretty much the same. I have to picture it in the way that these guys like make this gigantic detour, but they don't. Okay. Now we'll talk about regulatory cells as the last thing. Helper cells. Well, they help. How do they do that? So this is your helper cell. Okay, and it has T cell receptors. Which types of antigen presenting cells we just learned about? Antigen presenting cells. B cells. Let's start with B cells. Good. So B cell has MHC class 2 on its surface. Is that clear? Good. It presents the antigen. So what is the function of the B cell? No. It's, well, I can't argue. Yes, it is a minor function, but what is the major function of B cell? To become plasma cell and produce antibodies. Does that make sense? Now, T helper cell, by interacting with that specific antigen right here, will stimulate B cell to become plasma cell and produce antibodies. So it increases, we can call it increased B cell activation. Is that understood? Is that clear? Okay. What is another type of antigen presenting cell? Macrophage. They're dendritic cells, but they used for T cell education. Okay, macrophage. So it has MHC class 2. And there's an antigen on the surface. What's the function of macrophage? No, phagocytosis, right? Eat cells. Macrophage phagocytose things. So T helper cell, by this interaction, between T cell receptor and MHC2 on the macrophage will increase macrophage activity. Does that make sense? And the last response that it does, it produces chemokines and cytokines. Cytokines. And cytokines will interact with the receptors, cytokine receptors on CD8 cells, making them more effective killers. Okay? So it's CD8 cell activation. Does that make sense? I compare CD4 cells to the football coaches. The football team, can it play without a coach? Huh? New Orleans Saints about 3 years ago, without head coach, they have Drew Brees. They barely made 8-8 in that season. And they had a great team. Okay? So without a coach, they still can play, but it's going to be a lousy play. Does that make sense? So there will be no game. CD4 cell is that coach. It can coach B cells, it can coach macrophages, and it can give commands to the CD8 cell, which is essentially quarterback, right? Because if you don't have CD8 cell, you're not going to kill infected cells. You lose the key player. Does that make sense? Now, there's a disease that strips people. I'm sorry, my computer wants to restart, and I don't want it to restart. There's a disease that strips people of CD4. So if you get rid of CD4 cells, what's going to happen to your B cells? Huh? I just didn't hear. Yeah, the activity of B cells will go down, the antibody production will suffer. Activity of macrophages will suffer. CD8 cells may become anergic. I'm not going to ask this word in the exam, which means that they're not going to respond properly. They're not going to attack the infected cells. What is the disease? HIV, right? So HIV seemingly attacks cells that aren't directly dealing with the infected tissue. But it affects all types of immunity. Think about this. CD4 cells link cellular immunity, right, which is mediated by T cells, and adaptive immunity, which is, cellular and humoral, okay? So this is, we can say that this is the link between cellular and humoral. Humoral link. This will be the link between adaptive and innate, because your T cells are necessary for macrophage activation. Does that make sense? That chicken scratch. The whole system, yes, the entire immune response becomes much, much less active. That makes sense? Okay. The last thing to say is about these little outcasts, the T regulatory cells. What do? They regulate. You'd be surprised. They do regulate. Essentially, they dampen the immune response. Why? Why do you need to dampen the immune response? Once it's overactive, you cannot let it go uncontrolled. Because if it does, if it goes sort of for a long time without any limit, what it's going to start to attack? Yourself, and we call this autoimmune disease. Yes, that's autoimmune disease. Interestingly, well, and kind of expectedly, there are studies that show that number of T regulatory cells or activity of T regulatory cells in the autoimmune diseases, it's decreased. If you would look at the bowels of people with Crohn's disease, and you will stain for T regulatory cells, you can do that, specifically stain for T regulatory cells. What you're going to find is that people with Crohn's or IBD have less T regulatory cells in the mucosa and submucosa of the bowel than people without those symptoms. Does that make sense? Okay, so that's, and you know what actually kind of funny thing? We know so much about symptoms, you know, or signs, but we have no idea how it is regulated. So we know whether T regulatory cells are involved somehow. How to manipulate this? We still have no clue. Okay? It's not that easy, because you can't just throw it in. They have to home, that's an official term, home to a specific place. So, I mean, if somebody has inflammatory bowel disease, you can't just put T cells, T regulatory cells in the muscle, or just randomly in the blood, okay? And they have to be presented with an antigen to recognize the T cells that actually attack antigen and bring only them down, but not the entire system. So T regulatory cells, as you can imagine, they're very targeted as well. They targeted against other T cells, right? And only those that are activated now. All right? So I hope I gave you a general idea of what T cells do. I'm checking if got it covered. Okay? Is that more or less? Well, I'm so scared of not talking about things that I should. I think I got it. We talked about vaccines. Oh, now we go into the immunopathologies. What can be two types of problems with pretty much any system in the body? It doesn't function or overreacts. So we're going to talk about, okay, let's break the rules and talk about not working first. Huh? Well, when we say dysfunction, it doesn't work properly. So there are two types of dysfunction, right? If it doesn't work, or its activity is decreased, we call it immunodeficiency. Or if it works too hard and attacks your own tissue, that is what we call hypersensitivities. So we're going to start with immunodeficiency. When you get infected with, let's say, influenza, any type of disease, are you immunosuppressed? Yes, of course. I mean, look, if I'm fighting with you, like if we're fighting, I am much less likely to be able to fight somebody else at the same time. Does that make sense? So, if your immune system is dealing with a certain pathogen, it is much less likely to be in a full strength to resist another pathogen. That's why we learned that concept of secondary infection. When immune system is weakened, secondary infection can occur. Now, a lot of microbes can interfere with your innate immunity, but disruption of innate immunity is fairly rare. Okay? Does that make sense? Especially if we talk about congenital disruption. So immunodeficiency can have one of two flavors. It can be congenital or it can be acquired. So what does acquired mean? Developed, right? Got from something, okay? Which types of acquired immunodeficiencies, you know? Cancer. Now that one, well, cancer, if it's solid tissue cancer, it's going to be probably immunosuppressive at a certain point. If it's the blood malignancy, such as leukemia, then although you have a lot of white blood cells, your immunity is going to be down. Why? Huh? It's just going to be dysfunctional. It's just going to be bad white blood cells. Okay? Does that make sense? So cancer is one type of acquired immunodeficiency. Any other types? Based on type 2 diabetes? Well, it does. No, in type 2 diabetes you actually have high blood sugar, but you have inflammation, like systemic inflammation. So your immune system is definitely affected. We don't know, I wouldn't know the definitive consequences, like if you get a disease. Obviously, people with the diabetes are more prone to the lesions, but that's more because of the circulation problems. Okay. Mm-hmm.
So cancer weakens your immune system.
Mm-hmm.
After you acquire it, having a weakened immune system does make you more likely to develop cancer.
It's a great question.
Or a strong enough immune system, you'd be less likely.
There is, I don't know. First of all, we can't measure the strength of the immune system. So we can't say that Justin's immune system is stronger than mine. We know, well, we can't say that. Although it probably is because you're younger. We know that with age, overall resistance to infections declines. Okay? It is called immune senescence. That's why people if you had chickenpox as a child, you are likely to develop shingles after 55 if you don't get the vaccine. Because if what is walking pneumonia in a child can be a deadly pneumonia in 70-year-old. Does that make sense? However, in case of like what Hunter asked, if we had weakened immune system, are we more likely to develop cancer? One of the hypotheses, and hypothesis is something that you want to prove. This is more of a speculation about cancer. One of the speculations, ideas, that chronic inflammation is the prerequisite for cancer. Does that make sense? Trying to recall the example of chronic inflammation as the prerequisite for cancer. And endometriosis is the chronic inflammation of endometrium in the uterus. Okay, it is sort of a prerequisite, often precedes the development of the uterine cancer. Does that make sense? So there is an association. Is there a causation? We don't know, but there is an association. So you may see that your immune system is skewed to the wrong direction, it overworks, and obviously every person, a buddy of mine who worked in head and neck cancer department, his boss was like a big honcho in head and neck cancer, and his boss said, she said that every person at every given moment of time has 1 or 2 malignant tumors in the body. We have malignant tumors. Whether they're going to grow, okay, agglomerations of cells that can potentially become a cancer. Whether they're going to become or not, that's a whole different story. Immune system does a pretty good job by keeping them under control, destroying. Does that make sense? Got it? Okay, cancer, what else? HIV, AIDS. Well, one thing that I want you as future microbiologists to understand very clearly, HIV is not a disease. It's a virus. Human immunodeficiency virus. People can be infected with HIV and not have clinical disease. Either because they're in the latent stage or because they are being treated. Does that make sense? AIDS is acquired immunodeficiency syndrome. It's the full-blown clinical syndrome associated, not as caused by HIV, when CD4 cells are destroyed. Does that make sense? There's another condition. Question? Brianna, are you good? I thought you were skeptical about existence of HIV. Some people are. That HIV doesn't exist. It does. Really, there was a guy who. Huh? What? No, it's I showed MHC class 1 and MHC class 2, the presentation. It was the easiest way. Yeah, so the guy that actually suggested that HIV doesn't exist, he was told, okay, let's take a blood from a person with AIDS and do the IV injection in you, and then we'll see. He quickly refused. Another couple that suggested that HIV is a lie, they stopped taking antiretroviral therapy and they died of AIDS in about 2 or 3 years after they stopped. So, I mean, it's kind of a smart move anyway. Another condition that we rarely mention as acquired immunodeficiency is measles. It's a temporary, it's not forever, but measles infection, acute measles, and it's pretty much always acute, it kills all the B cells. It replicates in B cells. So for about half a year after you recover from measles, you walk around without humoral immunity. And then it comes back, but 6 months, okay? Congenital. When you're born, right? That's the condition that you have. And I mentioned before that it's rare not to have innate immunity. As far as I know, mutations in like neutrophil, genes associated with neutrophil development, of macrophage development, those mutations are lethal. Okay? Now, since we left with the adaptive response, there are 2 branches that are mediated by which cells? T cells and B cells. In terms of the deficiency, what options do we have here? Oof, don't throw smart words at me. In terms of the numbers of B cells, don't have enough or don't have, that's leukemia, that's cancer, but don't have any. So either you have a little or don't have any. Okay? Does that make sense? So if you don't have any, now throw smart words at me. A gamma globulinemia. A, no. Gamma globulin antibodies, emia in the blood. No antibodies in the blood. Okay? That's no B cells. There's a condition when the B cells, they mature, but they're not functional. It's called adenosine deaminase deficiency. You don't have to know that. Okay? Huh? Right, I won't. Now, if you don't have T cells, that's called DiGeorge syndrome. What do you think? What's going to be the worst condition? DiGeorge or a gamma globulinemia? DiGeorge. You don't have killers and don't have helpers. So B cells don't develop properly. Your macrophages are largely non-existent. Does that make sense? Can you lack both T and B? Sure. This is called severe combined immunodeficiency. Interestingly enough, mice with that syndrome, there are mice with SCID, you don't have to put them in some sterile condition. They survive pretty well in regular housing. Okay, probably you shouldn't sneeze on them directly, but they survive pretty well. So people with SCID, though, it's the acronym for this is SCID. People with SCID are known as boy in a bubble. If you Google boy in a bubble, there will be a photo of a boy. He's not in a bubble, but he's surrounded by the plastic curtains, and he's in a sort of a chamber that has positive pressure inside. So all sterile air flows around him and removes all the crap, all the pathogens, potential pathogens from his environment. I mentioned to AP 2 class there. I know about 2 cases when one boy was started on the course of immunoglobulins, so pretty much he got regular blood transfusions and managed to actually move out of the bubble and start to live more or less normal life. He died at the age of 30-something because of the renal failure. Blood transfusions. Low dose iron exposure killed his kidneys. Another boy got the bone marrow transplant, which makes a lot of sense, honestly, if you think about it. Because if he doesn't have T and B cells, you can give him somebody else's. And the donor was his sister. So he received the transplant, also in his teens. And everything went smooth until it turned out that his sister had latent Epstein-Barr virus. And when Epstein-Barr virus entered the immunocompromised recipient, like a person without any adaptive immunity whatsoever, it started to massively replicate and killed the poor fella in several weeks. Okay? There's no specific treatment. There was no specific treatment against Epstein-Barr at the time. Now we have. Okay? And so there were 2 boys. Then the same family with the second boy, they've got another boy who also had this syndrome, and that boy died at the age of 6 months. And then they got the third boy, who finally was healthy. So the fact that there were 3 boys in this story all got this disease and no girls, it's about this disease. Sex-linked. Dominant or recessive? Recessive, because 1 boy got healthy, you know. So women are carriers and men actually get sick. That makes sense? Okay, good. So for this, you have to be able to tell apart. What's the word? Acquired and congenital, yes. So if I give you the list, acquired and congenital. And the congenital features, like in this condition, patients don't have T and B cells. You have to pick the right condition. All right? Hypersensitivities. There are 4 types, and the first is type 1. The allergy. Here, how it works. So first, you have to encounter the allergen. An allergen is recognized by the B cells. Actually, by the receptor in the B cells. And B cells, what do they become when they recognize the allergen? They differentiate into, they will, another subset, plasma cells. And plasma cells will produce antibodies. Does that make sense? This will be some reason immunoglobulin E. Okay. And this immunoglobulin E gets stuck on the mast cell. That is the first exposure to the allergen. Does anything happen to you, like any symptoms of allergy during first exposure? No, nothing happens, right? And then this mast cell with immunoglobulin E on it gets exposed to the antigen second time. So it's primary exposure, that's secondary exposure. You understand that those IgE that are stuck to mast cells now recognize the allergen. What happens to the mast cell? I didn't tell you this. Mast cell cannot. It contains the granules. With what? Histamine. It starts the granulation. And degranulation means that histamine is being released. And if you don't mind, I don't want to put the symptoms on the board. I'm not going to ask you about symptoms, not a P class. But what happens to us? Okay, we get stuffy nose. Stuffy nose. Why do we get stuffy nose? Histamine stimulates what type of response? Inflammation. Right. Now, in inflammation, what happens to the diameter of the blood vessels? It goes up, so blood flow to the nasal mucosa increases. What happens to the vascular permeability? The ability of the blood vessels to let fluid through. It increases, right? So more fluid goes through the blood vessels. and more fluid goes from the nasal plexuses into the mucus in the nose, and you form watery secretions. So you get stuffy nose. Same happens in the lacrimal glands. So produce more tears, and they cannot drain into the nose because mucus blocks the lacrimal ducts. In the skin, you get little inflammatory foci, which are called hives. Okay? Now, if you're really unlucky, and you get itchy, because histamine will interact with the pain receptors on your nerves. Receptors for pain and for itchiness are the same receptors. Okay? That's why when we rub we hit something, rub it. When we rub, we kind of block the sensation of pain. Okay? And if somebody's unlucky and allergen binds to all the receptors in all the body, in all basophils and mast cells, and they all degranulate at the same time, and the load of histamine is released in the blood and the tissues, we have anaphylactic shock. Drop of blood pressure due to the vasodilation, asphyxia due to the constriction of the smooth muscles in the bronchioles, swelling of tissues due to the massive edema everywhere. Okay? Does that make sense? So that's allergy. How can you prevent allergy? Okay, what you can do about it. Let's not say prevent. What you can do about it. Oh, wait. Not altogether. Not altogether. Medicine. Take allergy pills. Black histamine. Antihistamine. So when should I have an allergy to cats, and I want to visit my friend who has cats. When should I take Claritin? The day will be too far, it's 24 hours, but before, yes. I usually take even 2 hours fine. Zyrtec or Claritin, they both... Huh? It's fine. And I did that experiment on several occasions. If I forget to take it and then take when I'm there, it doesn't help that much. Because I'm usually fine when I'm home, but I'm suffering when I'm there. Okay? What else can you do? Can you stop the inflammation? Corticosteroids, just take prednisone. I mean, I'm not saying that it's a great idea to do it every time you have an allergy, but it's definitely on the table. There's another option. You can address the issue and start to desensitize your immune system. No, they're too lovely. They're too lovely. But you can expose yourself to the low doses of the allergen and increase them over the period of time. I'm not allergic to kittens. That's interesting. That's not a good argument about doses, because here's the thing. Actually, if you speak about allergy, often when I say I'm allergic to cats, what does that mean? Does it mean that I'm allergic to a component of the sweat or a component of the skin? That's or maybe saliva, or maybe something else, because I definitely have different symptoms if I'm exposed to different cats. I can be in some houses without observable problems if I don't touch the animal. In others, I enter, and in 15 minutes, I go home because I'm a mess. Okay, so when people say I'm allergic to something, I'm allergic to apples that are sold in any grocery store. Okay, but not to the farm apples. It depends. Now, the exposure to the small doses. Kittens is fine. I mean, you bring the kitten and you rub it in your nose. I can pet cats, but then I must not touch anything that can eventually touch my face. Does that make sense? So I can't hold a cup, because it will touch my lips and it will end up on my face and I will have runny nose and oh, God forbid, no. That's absolutely, that shouldn't happen ever, okay? So exposure to the small doses. There were studies showing that kids who have peanut butter allergy, if they're exposed to small doses of the protein they're allergic to, they become more and more resistant, not to the extent that they can eat it, but to the extent that they can tolerate it. They can be in, like, well, probably not traces of peanut butter in the food. But, you know, sometimes I've heard stories about people becoming swollen if somebody eats peanut butter next to them. I don't know how true is that, but okay. Yes, yes. My good friend was on the flight, I think it was Delta, and he had a pack of peanuts that he bought at the airport. And the flight attendant approached him and said that he should get rid of that packet or put it somewhere else because there can be people with peanut butter allergy on the flight. And he said, well, maybe they are, but I seriously doubt that if I will drop one peanut on the floor, that person with peanut butter allergy immediately jump and scavenge it. Nevertheless, they forced him to remove the peanuts. So you can slowly, I bring up, since I have a control and experiment, I have one child with allergies and another child without. The guy with allergies was allergic to milk. It was pretty bad skin allergy. And then through the years, you know, when you go to school, when you go to friends' houses, you're going to get exposed to the milk. If you're not drinking milk, you're going to eat ice cream, okay? So he got exposed to very small doses of milk through the years, and now he can have like a glass of milk every day, and he's not going to develop any eczema. Does that make sense? So we kind of involuntarily expose them to small doses. Let's take a break, and when we'll go back, we will review the quiz and look at our results.